My name is Rachel Beattie. I'm a student at Mass Bay Community College. I'm in the middle of a career shift to become a high school math teacher, and I've been taking some background courses at Mass Bay this semester, including differential equations. And I'm going to do a brief presentation on something I've been working on in differential equations. This is a presentation on the Dirac delta function. That is a function that helps to model sudden impulses. Paul Dirac, a theoretical physicist, introduced this function in 1930 for quantum mechanics, and it's been found to be useful in a wide array of circumstances. For example, if there's a large force acting in a very short period of time, like a bat hitting a baseball. I'm going to go through a couple different types of problems where it's been useful. The function models an impulse by assuming that the force is instantaneous and takes an infinite value for only one point in time. So there's a model if you take it from negative a to a around 0, and the force that acts that entire time is 1 over 2a, then the area is equal to 1. So the thought experiment is what happens as a gets smaller and smaller, gets closer to 0, what happens to the height. And the idea is that as it gets closer to 0, the height goes to infinity. This is the idea behind the Dirac delta function. It's defined as having the property that it's at the point C, it's infinity or infinite, or it's 0 otherwise. But that the area, when you integrate it, is equal to 1. This, strictly speaking, is not a function in the traditional sense. Wouldn't work in calculus because a function that is 0 everywhere except at one point must have an integral of 0. But it is a useful ad hoc tool to model situations with sudden shocks or large impulses. Integrals are fairly straightforward because it's defined as 1, so and 0 everywhere else. So if you multiply a function by the delta function, you get 0 everywhere except for the point C, and then you get, it's as if you shifted up the whole function and you get f of c. The Laplace transform is also very straightforward and very helpful for solving these sort of problems, that the Laplace transform is straightforward. Because the derivative is 1, the Laplace transform is e to the negative cs. Here's an example of a first-order differential problem. This is the classic salt in the tank problem. There's 5 gallons of a salt solution with 2 pounds of salt per gallon. Fresh water is flowing in at 1 gallon a minute. Mixed water is leaving at 1 gallon a minute. After 6 minutes, 4 pounds of salt are instantly dumped into the tank and instantly mixed. So model level the salt as a function of time. And this is where the Dirac delta function comes into play. You have the change in salt, y prime, and it's a function of the rate in and rate out of the salt coming in, which is 0, and going out. And it's also a function of the delta function at time 6. You use the Laplace transform, and what you get out of it is a unit step function, which is interesting how it's tied to the unit step function. You get the e to the negative 6s gives you the unit step function, which means basically that there's 2 functions. There's one function up to time 6, and then there's that function plus another function after time 6. And you can see what this looks like in a graph. The salt is declining because it's fresh water coming in, so it's declining until time 6, and then there's a discontinuity and the quantity of salt increases. Here's a second example. It's of a second-order differential equation. This is the classic spring mass system. There's a mass and attached to a spring, and the spring is stretched to 20 centimeters. And at time t equals 0, the body of mass is pulled 20 centimeters below its spring body equilibrium, and then it's released. And then after 3 seconds, it's struck in a downward motion by an impulse of 3 kilograms per meter second. So you can see the second order differential equation that you get from this. Y of 0 is equal to 1/5, and y prime of 0 equal to 0. On the right-hand side is the impulse part of the equation, the 3 delta t minus 3, shows there's an impulse of 3 at time t equal 3. When you take the Laplace transform, you get the 3 equal negative 3s, which is the component that's going to get you the unit step function. When you take the inverse Laplace transform, you get the unit step function. And I'm going to move this out of the way. The first component in that equation is the cosine. It's a system that has no dampening, so it just oscillates. The cosine function, it's oscillating. And then the second half is what happens at time t equal 3. There's an additional oscillation added. I can show you here what that looks like. In this case, the function is continuous. However, note that there is a kink at time t equal 3 when the impulse was delivered. Because of the additional force added, the spring begins oscillating with a larger amplitude. Here's another example, another spring mass dashpot system. This one has an initial upward velocity and then 2 impulses striking down on it at time t equal 2 and t equal 4. That's the differential equation. So you can put multiple delta Dirac functions on the side. And don't have time to go through all the steps here, but you apply the Laplace transform to the entire equation and you come up with 3 terms that are for the 3 time periods from time 0 to time 2. And then there's the additional function from time 2 to time 4. And then there's additional function from time 4 and beyond. And I can show you what that looks like over here. You see here the initial upward motion, which is dampened, and that's negative. And then the 2 subsequent downward impulses at time 2 and 4, which are also subsequently dampened. These are examples of an external force applied for a very brief period of time. As we've seen, the Dirac delta function is very helpful under these circumstances, even though it's not technically a function. When you use the Laplace transform, you can find valid solutions for a wide variety of problems. The Dirac delta function is useful in a wide array of circumstances in mechanics, in electrodynamics, quantum mechanics, and mathematical statistics. In the natural world, there are many circumstances where a sudden force acts in an instant, and the Dirac delta function provides a practical method to model this. I appreciate your listening to my presentation. Thank you. Bye.